to explain to you our last material, which is how to find the best hyperplane. Okay, so this one is actually our problem. So the problem is classifications. Okay, we would like actually to find how to classify between these two data. Let's say this one is x1 and this one is x2. Okay, and then we would like to separate between data with category A and B. Let's say this one, this cross one is a A, and then the circle one is a B. We would like actually to draw a line. Which line? This line. Okay, a line that is okay. This is not so good. I will try to do all my best. Let's say this one. Okay, this is the line that we would like to draw. This is best hyperplane that we would like to calculate. So what is called by best actually? So the best in the basic of the SVM is actually when you find the largest, what we call as margin. So what is actually margin here? Sorry for this is not quite straight. Okay, so this one we define as margin. So best hyperplane is actually largest margin. Okay, so how do we do it? So our topic today is actually just very simple. We would like to define what is margin and then how to optimize it with respect to, in our case, it is hyperplane, which is in this case it is a line. So we'll let us refresh again your ideas, our idea. So what do we call as a, let's say this is a G, okay? This is G is a line that is defined by what we know in the junior high school. It's a line is defined as this one, mx plus c, okay? This is exactly the same as another notation. I call it as a w1x plus a, and then we can also write down as a w1x plus w0. Okay, in this case, okay, in this case, we define the line as, call it as g. This is w1 x1 plus w2 x2 plus b. Okay, so this is my definition now. It's a line exactly the same. Okay, this is x1 belong to, let's say this is x, and x2 is analogous with y. And then now actually we would like to separate this between A and B, class A and class B. So what do we do? Actually, to separate that, so that so we choose actually. So we define in class A, we define W1 x1, W2 x2 plus B. In this is if x1 and x2 belong to class A, and then we define it as a positive. Okay, for points that are in plus 8. Let's do it. Alright, and then this is belong to 8, class 8. Okay, and the other way around. So if this points belong to 8, then this is the line itself is positive. In the line, I mean these definitions. Okay, and then if this is in the B, they are in the B, class B, then this is negative. Okay, x1, w2, x2, this is I plus b. So this one is negative 4, x1 belong to x1, x2 belong to class B. Okay. Now we would like to simplify something. Now we try to define, to simplify actually first. We would like to simplify the definitions of those lines. Okay, look at this blue circle. This is actually the nearest class B to the point. Okay, this one. This is the nearest point of the B, and then the other one, let's say this one. Okay, this red one, the cross one, is belong to class A. Is actually the nearest point in class A that with respect to the line, the green one. Okay, so this one we define. Now we define. Let now let xi, x1, x2 plus. Okay, this is plus. So this one is actually the coordinate of this one is x1, x2 plus. Okay, this one is plus, and the other one, the blue one here, I call it as x1, x2 minus. Okay. So now let x1 is, and then x1, x2 minus minus. These are actually nearest point in class A and class B respectively. To line G. Okay, so this one is the nearest, and then this one is nearest. So without loss of generality, without loss of generality, we define the following. Okay, so I define as follows. W1 x1 plus, okay, and W2 x2 plus. So this one are in class A, plus B. This is actually 1. Okay, this is in class A. This is the nearest point in the class A, and then the nearest point in the class B. This is x1, this is minus, and W2 x2 minus, this is plus B, and in the class B, this is minus 1. Okay, did you notice? And so this one, this is for the every point in A, and this one is every point in B. Okay, but the nearest point for x1 and x2 plus, it resulted 1, and then nearest point in the B resulting minus 1. Okay, what does it imply? So so that we have actually, so we have, what do we conclude from this green one? This is the one to this one. It's actually, we have what w1 x1 I, w2 x2 I plus b for xi x1 I x2 I element. If this one is element A, so that what does it mean? So this one is actually larger than 1. And then the other way around, x1, x1, w1, x1, I, w2, x2, I plus b. This is less than minus 1 if this point belong to plus b. Okay, so we have actually defined what is class A and what is class D by these definitions. Okay, so let us review. Okay, we would like what is our aim actually? We would like to generalize, okay, this point. So we would like to maximize what we call as a margin. Then this margin actually depending on the line. The line itself is defined by this one. Okay, load. So let's go back to our main aim. Our main aim is actually uh, let uh, let the distance between and G to nearest point, which is x1 plus, x2 plus, this is an A, and then x1 minus, x2 minus, this is in B, this is A, and this is B. Okay, let the distance between G to this nearest point, A and B, as what we call as a G, and here's this case, we define as this one. Okay, we know from this part, that this, sorry, w1 x1 plus w2 x2 plus b. So, and then divided by its the distance itself, which is square root of w1 square w2 square. This is actually what do we have now? This is actually 1. Okay, so we have this 1 divided by, this is actually the radius of this the radius of the weighting parameter, w1 and w2 exactly the same, w1 square w2 square. Okay, and then in the class B we have w1 x1 minus w2 x2 minus plus b. Okay, and then this is divided by the same things as 1 square w2 square. Okay, now we have defined actually j. Okay, look at this one. We have conditions that are two conditions, but it is only differentiated by minus and plus. Okay, why don't we simplify things? So we eliminate these two into one. To that end, okay, we define some function, or we call it as a j, y, yi. This a function that is in its input is actually the coordinate itself, x1 and x2 I. This is ij. So this one is actually just to differentiate between minus and positive, positive and negative. So this one is actually the sign of the x1. This is x1 I, x2 I. Okay, what is the sign? This is positive when x1, x2 belong to, this is belong to class A, and then this one is a minus, y is minus when uh, x1, x2, this is I belong to class B. So that that we have the following. Okay, so we eliminate these two into one formula. I use blue. Let's say I use blue. So we have one W1 X1. This is I. W2 X2 element I plus B times. Now we have times with Y I. Okay, yi, this is positive. This is for I, 1, 2, and then the number of data, n. So we have eliminate actually to inequality to be 1. Okay. So what do we have so far? So far we have defined the margin, the distance, okay, 1 over something. And then we have defined the double relation between W1 and W2, which is this part. Okay? So what do we have now? Let me repeat, okay? Let me repeat. So we actually aim to get the best hyperplane. In this case, it is the baseline to classify between it is class A or class B. Okay, the hyperplane itself is a line, which is defined as this G. Okay, our aim is to find G that makes such that the largest, such that the margin is large. Best one. Okay, so what do we have? We have already defined the J, and then we have already defined the line itself. Now the problem, okay? So this one is actually the constraint problem. What is the constraint problem itself? It is actually find best hyperplane, which is in this case is line. Okay, what do we want or would like to find? Find the line, actually the line G, okay, such that we have largest margin. Okay, so this is the aim itself. So what is the largest margin itself? It is actually 1 over W1 square, W2 square, which is actually it's J. Okay? We would like to maximize this one. Okay, with respect to, of course, in this case, it's W1, W2, and B. Okay, so this one is our argument. Okay, but W1 and W2 depending on each other, and then it has to satisfy something, which is this part. Okay, so this one is subject to, okay, or ST, okay, call it S. So this one, the W1 should satisfy W1 X1 element I, W2 X2 element I, and then plus B, and then times everything by yi should be larger than 0. So for I So 1, 2, until number of data. Okay, so what do we have so far? We have defined problem statement. What is the problem statement? So this one is actually what in mathematics we call it as objective functions. What do we the things and the function that we need to optimize? Okay, and this one is actually constraint. Okay, so far, so far so good. Okay, now let me rewrite this maximization problem into minimization problem. Okay, to that end, I would like to remind you that, or to make a simple analogies with some intervention. Okay, so if we have 1 over a, and then we would like to maximize this, what does it mean? Value of a, sorry, value of 1 over a is actually maximum when is it? When a is smaller than a smallest. Okay, so what does it mean? This problem is actually equivalent with minimizations of a itself, or exactly the same, minimizations of a squared, exactly the same. Okay, so I would like to rewrite again this one. So I will write this maximum maximization problem into minimization problem. Minimization problem with respect to what? W1 square, W2 square. Then I put a half in it because it's much easier when we derive it, when we try to make to find the minimizations of that. So it's two cancels each other. Okay. So this one is argument is exactly the same. Okay. The argument I define it as a minimization problem, and this one is subject to the same thing as this part. Okay, subject to W1 X1 sorry, this is X1 W2 X2 at I component. This is a B, then times Y I larger than 0. So I have reformulate our maximization problem into minimization problem. Okay, that's clear. I hope it's clear. So this